Hi, good evening. We are getting into lesson 10.2, which is all about exponential growth and exponential decay. In real world, you have a lot of phenomena that happens, which can be modeled using an exponential growth or an exponential decay function. Both are exponential functions, but one is a growth function, the other one is a decay function. All right. So in the introductory lesson, we saw the animal cell division, right? That is an example of an exponential growth function. There are other examples like that. I could call the money that I put in a bank that is gaining a compound interest every year or every month or every quarterly or yearly, whatever it is that I'm talking about. The money that I put in a bank that is earning a compound interest is an example of an exponential growth function. Also, the population growth of a town that can be modeled using an exponential growth function. The growth of microorganisms in a petri dish that can be modeled using an exponential growth function. What is an exponential growth function? You have something, say a few microorganisms, or you have a little amount of money, or you have a few number of people in a town that are growing in number. All right, so they are growing over time, right? You're allowing it to grow. You have some amount that you start with and you're allowing it to grow. When it grows exponentially. So there is a percentage growth, the percentage rate of growth every year or whatever the time period is. All right. So that's an exponential growth function. Similarly, exponential decay also, you're starting with a certain amount, whatever be it, money or number of people or number of cells, whatever is it that you're starting with. Over a period of time, you are losing something that is exponentially. Okay, so you're losing that amount exponentially. Okay, so that's an exponential decay function. So both exponential growth and exponential decay, let's take an example for an exponential growth function. Say let's consider the population of a town. Say there are 1,000 people to begin with. Okay, at the beginning of year 1. So I'm trying to find the population growth, how much there will be, how many people there will be after a certain period of time, say over 10 years. After 10 years, how many people are going to be there in that town. So what they have given me is the town initially started with 1,000 people. All right. So that means that's when the period has started. Whatever I'm looking at, the data that I'm looking for, the period has started. So at the beginning of year 1, I have 1,000 people. Okay, so the growth rate they are talking about, growth rate means how it is growing. How are the people growing? The number of people. Okay, so they're saying the growth is 50%, right? So the growth rate is 50%. All right, what do I mean by that? If I had 100 people, I'm adding 50 more people the next year. All right, so that is 150. That's 50% of whatever it was. So now I'm not starting with 100 people, I'm starting with 1,000 people, right? So the beginning of first year, that is beginning of time, I'm going to make a table. The beginning of year 1, this is the number of years that's passed. Okay, and this is the number of people. Okay, so beginning of first year, no year has passed. I start with 1,000 people, right? So end of first year, end of year 1, I started with 1,000 people. I'm adding, how many I'm adding? 50% of what I had. So 50% of 1,000 is 500. So I added 500 more people. I ended up with 1,500 people. At the end of first year, I have 1,500 people. Now year 1 has ended and year 2 has begun. So the beginning of year 2, I have 1,500 people. So end of year 2, I started with 1,500 people, beginning of year 2. End of year 2, I'm adding 50% of that, which is 750. So I have 2,250. So end of year 2, I will have 2,250 people in that town. So year 2 has ended and year 3 has begun. In the beginning of third year, I have 2250 people, and the end of year 3, I'm going to be adding some more people, right, during that third year. So 2250, 50% of that I'm adding, which is 1125, which will give me 3375. So third year, it is 3375. So I can keep on doing that, but if I understand the pattern and I write an equation for it, I can find the number of people after any number of years, say 10 years or 25 years or 30 years, okay? So I can find the number of people for any number of years. So that's what that's what my goal is, all right? So first, before I get into writing an equation, I want to know what kind of function it is. It's not a linear function because I'm not adding the same number of people every time. First year I added 500, second year I added 750, third year I added 1125. So I'm not adding the same number every time. So that means it's not a linear function. So let's see if it is an exponential function. For it to be an exponential function, I should have a common ratio between the consecutive y values. All right. So the common ratio b. Okay. So what is the ratio between these two y values? So 1500 y2 divided by y1, 1500 divided by 1000 is going to give you 1.5. So if I multiply 1000 by 1.5, I'm going to get 1500. So the ratio has to be common between all the consecutive y values. So 2250 divided by 1500. Okay, y2 divided by y1 will give you 1.5. So 1500 multiplied by 1.5 is going to give you 2250. Third, again, I'm going to check 3375 divided by 2250 times 1.5. So 2250 times 1.5 is going to give you 3375. As I can see that the population is growing, right? And it is growing exponentially. That's why it's an exponential growth function. All right. If I want to write an equation for this, start with f of x equal to a times b to the power of x. Here we are going to change the letters a little bit because it's always to do with time. The growth and decay is always to do with time. So my input is time. So instead of x, I'm going to use a t. So f of t equals a times b to the power of t. T represents time. All right. And we're going to change a little bit. This is the standard equation for your exponential function, right? So we're going to rewrite it specifically for an exponential growth function. Okay. So let's go ahead and write the equation. We know that a is our initial value. So initial value is the number of people that you begin with. So to begin with, I had 1000 people. So my f of t is going to be 1000 times, we found that our common ratio is 1.5, right? So it's going to be 1.5 to the power of t. So this is my equation, which is easy for me to write if I could make that table, or if I understand what they're talking about, right? So it's not going to be this easy like 1000 people and 50%. You're able to do that, right? So there is another way that we can figure out. This is always going to be given to you, this 1000, which is the number of whatever amount that you're starting with, your initial value. But figuring out this common ratio, how can I figure out this common ratio? One way to figure out is if you can make that table, you can figure out your common ratio. But there is an easy way. So we saw that the population growth is 50%, right? That means I had the 100% of people, which is 1000, and I'm adding a 50% to that, which is that 500. So together I got 1500, right? So 100% is a whole and 50% is 0.5. All right, 100% is a whole and 50% is 0.5. That's how I got that 1.5. So the 50%, that data is given to me in the problem. They are telling me that's my growth rate, right? So 1, so this is my B. B is 100% plus 50% because it's a growth. So B is 1 plus 0.5 or 1 plus the rate of growth, 1 plus the rate of growth. Rate of growth is usually represented by the letter R. So I'm going to write B is equal to 1 plus R. 1 plus R means R is a number that you rewrite the percentage as. Okay, so the 50% is given to you, the 50% rewritten as a number. So that's a 0.5. Okay, 50% is 0.5. So that's how you got your common ratio as 1.5. So if I have to rewrite this formula, f of t will be equal to a times b is 1 plus r to the power of t. This is what you see in your textbooks. Okay, 1 plus r to the power of t. So let's write it. This is my final amount at the end of any time period. Final amount. This is my initial amount or initial value. Final amount or final value. This is my time period. What is it that I'm looking for? The time period. And R is the rate of growth. Rate of growth. It will be given to you as a percentage. You got to rewrite it as a decimal number. Percentage written as decimal number. Okay. So as you can notice, for my exponential growth, your B has to be greater than 1. Otherwise, there is no growth. The B has to be greater than 1. The B is called the growth factor. We saw that it is a multiplication factor, right? So in this case, specifically, it is a growth factor. So it has to be greater than 1. And so that's why I'm adding the percentage growth to 1 to get my growth factor. So this is a general equation for your growth function, exponential growth function. So I'm going to make a separate video for exponential decay function. It's not going to be this long because you already know the concept a little bit about what an exponential growth is. So exponential decay is just the opposite of it. Instead of adding it to a 1, I'm going to take it away from the 1. That means I have 100%. It is decreasing by a certain rate. So I'm going to be subtracting it instead of adding. So I'm going to get a decay function. Okay. So let's take a look at what an exponential decay is in the next video.